Okay, Bismillahirrahmanirrahim. Dear students, today we will start a new topic, and that is a very important topic. In fact, it's an application of what we are doing last time, that is about the normal mode analysis. Now, in the normal mode analysis, we have talked about 2 degree of freedom systems and how we can find the natural frequencies and mode shape of these 2 degree of freedom systems. Today we will study a very important application of the normal mode analysis, and that is normally called as undamped vibration absorbers. Undamped vibration absorbers. Now, the modeling of this undamped vibration absorber is actually based on what we are doing for the 2 degree of freedom translational mass spring system. And why? Because because it's an application of 2 degree of freedom system, so that's why the most of the modeling is based on what we are doing last time. So it's very important to understand the last lecture so you can understand this lecture as well. Now, in some times it's also called as tuned mass damper. It's basically the same thing. It's not actually a damper like we are doing, what we are studying for last many weeks, that is about viscous dampers. It's called mass damper, which means the mass act in such a way that try to reduce the vibration. So it's normally called as tuned mass damper or undamped vibration absorbers. Both words are used. Some you typically use tuned mass dampers, some use actually the word vibration absorber, but both actually have the word for the same phenomenon. Okay, before going into the detail of this, first I will show you some video and some pictures in which absorbers have been used and how they are used. Before that, we just try to understand the concept that why we use vibration absorbers. So, for example, if you have because we are talking about an undamped vibration system, so we have K and M. And why we are talking about undamped? Because the damped vibration absorption modeling is quite complicated as compared to the undamped. So for your case, it's an undamped vibration absorber. In most of the cases, we actually use undamped, but in few applications, and I will elaborate in the last part of the lecture, that in few applications you required a damped vibration absorbers. In very few applications, and that is what are those applications I will discuss in the last part of this lecture. Okay, so let's say we have a spring K1 and mass M1. Now let's say if there is certain force is applied, let's say it's something like F0 sine omega t, as we are doing in forced vibration. So this is, if you can summarize this, it's an basically a forced vibration system. Clear? Now this is K1 and M1, and let's say a force is applied on the M1, like there's an unbalance, or maybe due to a wind, or maybe earthquake. Like if I just draw, if you try to visualize it physically, so let's say we have a machine and we have an isolators, for example, like we are doing in the base excitation, like we have, let's say, 4 isolators, and there could be more than 4. And let's say there is an unbalance, there is some rotating disc and there is an unbalance. So because the rotation of this disc, it creates vibrations. So the F0 is nothing but me omega square. Clear? So you actually design isolators. So these are isolators. Sometimes use dampers as well along with the springs, but these are called isolators. These isolator isolates vibration, so the minimal vibration will transmit to the base. Now, for example, you also want, now in some applications you can't remove the source of the force, as I told you before. Like I told you, one example is case of hammering in the cement plant. That's very difficult to reduce those vibrations, and in other applications like in engines you can't reduce the vibrations because there are unbalanced forces. So for that scenario, so for that particular scenario, you actually want to reduce the vibration of the main mass as well. So you want to reduce the vibrations of main mass. The one way is the try to increase omega by omega n greater than 3, so that you can reduce the vibration. This is a one way. Second way is to increase zeta so that you can decrease the vibrations. Now in most of the applications, sometimes it's very difficult to increase omega by omega n, and so sometimes it's not possible to increase omega by omega n. Secondly, if you increase zeta to a very high value, system become more stiff and it can produce cracks. Now in certain application in which you can't increase omega by omega greater than 3, which is your first priority, that if you want to reduce the amplitude of either, for the first thing is try to reduce the source of that vibration. If you can't remove the source of vibration, then try to keep the frequency ratio greater than 3. But in, as I told you, in some cases it's very difficult to even change omega and omega n, and that is very sometimes operates in a very close range. Even you can't control, in some cases you can't control omega as well. Now in certain cases there is a one solution. If you can't do both, you add vibration absorber. You add vibration absorber or tune mass damper. It's the same thing. So this is a third case, and in most of the real time applications we actually go towards the third solution, in which first and second solution is not feasible. Second solution is not a feasible solution because increasing zeta ultimately will will make the structure stiffer and hard to move. Now in those applications in which you actually can't change the frequency ratio, that is omega by omega n, then you actually add a tune mass damper or vibration absorber. So this is our actually the main task today. Okay, so what is a vibration absorber? So I just rub here. So what is a vibration absorber? You add a second mass spring system, that is K2 and M2. So that is with the attached to the, so K2 is attached with the M1, and the one end of the K2 is attached with the mass and second with the spring. Sorry, one end of spring attached to the M1, other to the M2. So this addition is called as vibration absorber. Now the word indicates, if you look at the word indicates vibration absorber, means it tends to absorb the vibration of the main mass, which is M1. The main mass can be machine or any building or whatever that is. So it tends to reduce it in such a way that if omega, which is the forcing frequency of this force vibration coming forward, the force from any source, become equals to omega 22, which is and omega 22 is the individual natural frequency of the absorber mass and spring, then typically your let's say it's for example, let's say its vibration is x1 of t, this is x2 of t, like we are doing in the normal mode analysis. Now by adding an okay, so it's try to reduce x1, which is our main target. So and how do that mathematically, I will just perform the modeling so that you will understand. My claim is that if omega is equals to omega 22, x1 become very small, and how do you know that becomes small? That is because of the mathematics that you do behind this. So we will see what mathematics actually reveals us. So first we will do the mathematics, and then I will show you the real time applications of what is going on. Okay. So by adding us K2 and M2, this system becomes 2 DOF system. initially it's a 1 DOF system. Initially it's a 1 DOF system because there is only M1 and K1. By adding an absorber, which is absorber is nothing but K2 and M2, the stiffness and the mass. So the system become 2 degree of freedom system. Now to write the equations, so it's the same method that we are doing in the normal mode analysis. Equation of mass 1, same method, which is M1 x1 double dot equals to, so minus K1 x1, and because spring is K2 is attached between two, K2 x1 minus x2. Okay, because force is also applied on M1, and because it's an external force, we have to write with the plus sign, F naught sine omega t. In the monomode analysis, we are not considering any force, but in this case, we have to consider any external force, and because with the plus sign, because it's an external force. Now, equation for mass 2, and that is M2 x2 double dot equals to minus K2 x2 minus x1. So we have only one term because there is no spring beneath, no spring, so we have only one term. Okay, so just rearranging this, we have actually used the same philosophy that we are doing solving the normal mode analysis, the 2 degree of freedom translational vibration system. So this is M1 x1 double dot plus this equation, I'm writing about this equation, plus K1 x1 plus K2 x1 minus x2, because force is plus, so we keep it on the right hand side. Clear? So separating the two terms, so x1 and x2 terms, so we have plus K1 plus K2 times x1 plus minus K2 times x2. It's the same thing that we are doing last time, equals to F naught sine. The only difference is now right hand side has some force. This is, you called it equation 1, and just solving this equation, rearranging this, so we have M2 x2 double dot plus separating x1 and x2 terms, so we have plus, in fact is plus minus K2 times x1 plus K2 times x2 equals to 0. This is our two equations. The same thing that we are doing in normal mode analysis. Now we try to solve these equations further. So just putting, so as I told you, let x1 equals to some capital X1 sine omega t, where capital X1 is an amplitude. Before that we are writing is as A1. So if you write A1 and X1, doesn't make any difference. X2 is some x2 sine omega t. Just taking the derivative, so it's x1 omega cos omega t, and x1 double dot is nothing but minus x1 omega square sine omega t. Similarly for the x2 dot, it's x2 omega cos omega t, and x2 double dot is nothing but minus x2 omega square sine omega t. Putting the values in the previous equation 1 and 2, so it become m1 into minus x1 omega square sine omega t plus k1 plus k2 into, what is x1? It's capital X1 sine omega t plus minus k2 times x2 sine omega t equals to f naught sine omega t, and second equation is m2 into minus x2 omega square sine omega t plus, in fact it's minus k2 times x1 sine omega t plus k2 times x2 sine omega t equals to 0. So these are the two equations. So dividing, so we call it, let's say, equation 3, and we call it equation 4. dividing equation 3 and 4 by sine omega t, what you get is minus m1 x1 omega square plus k1 plus k2 times x1 plus minus k2 times x2 equals to f naught, because sin omega t also omits from the right hand side in equation 3, so we call it equation 5, and minus m2 x2 omega square plus minus k2 x1 plus k2 x2 equals to 0. So we call it equation 6. Why 0? Because force is only applied on the m1, not on m2. Again, by using the same philosophy, that just combining in terms of x1 and x2, you get minus m omega square plus k1 plus k2 times x1 plus minus k2 times x2 equals to f naught. This is called it, you call it equation 7, and minus m2 omega square, sorry, minus k2 times x1 plus minus m2 omega square minus k2, sorry, not plus k2, yes, x2 equals to 0. So we call it equation 8. So we have separated x1 and x2 terms, the same thing that we are doing in the normal mode analysis. Now writing in the matrix form again in the same way. So matrix says it's minus m1 omega square plus k1 plus k2 minus k2 minus k2 minus m2 omega square plus k2 into x1 x2 equals to f naught 0. Now if you remember from the previous lecture, the right hand side is 0 0. Now there is an f naught. Why? Because there is a force applied at the m1. Now we are actually in this case in the design of vibration absorber, we are interested in the expression of x1 and x2. If you remember previously, also we have find out in the previous cases the ratio of the amplitudes, but here we are interested in finding the equations for x1 and x2. For that, you know that if you want to find x1 and x2, you have to use a Kramer rule, and the Kramer rule says that x1 is equals to, if you replace the first column by the f naught 0, so the determinant f naught 0 into minus k2 into minus m2 omega square plus k2 divided by the determinant of this matrix, which is minus m1 omega square plus k1 plus k2 minus k2 minus k2 minus m2 omega square plus k2. So we have this matrix, and for the x2 we have, if you just replace the second column of this matrix by f naught 0, so it become minus m1 omega square plus k1 plus k2 minus k2, and the second column is f naught 0 divided by the same matrix. Okay. So these are the two expressions for x1 and x2, and you know this by the Kramer rule. Okay. So we are actually interested in x1 and x2 expressions, so that's why we have actually find out the expression for x1 and x2. Now we have to solve it to get the actual relation for x1 and x2. For that, x1 is equals to, if you multiply f naught into minus m2 omega square plus k2, I think so, just verify it from the last step. Okay, yes, divided by, and if I multiply the determinant, it become minus m1 omega square plus k1 plus k2 into minus m2 omega square plus k2, and minus, you get minus k2 square, minus k2 square. So first you solve for x1, then we will go for x2. Okay. Okay, if I take this x2 common, so if just simplify the above and below terms, so just simplify f naught m minus m omega square is m2 omega square plus k2. इसको we have simplified it. So if we take k2 common out of the bracket, so it come f naught k2, and this become minus m2 omega square over k2 plus 1. Okay, if I take m2 in the denominator of k2, which I can by using mathematics, so it's become 1 minus omega square over k2 over m2. Now k2 over m2 is nothing but the individual natural frequency of absorber mass, which is k2 and m2. And again repeating, in the Thomson book it is written as omega 22, that is the individual natural frequency. It means that if you remove k2 and m2 from the main mass and then measure its natural frequency, it's k2 over m2, as we are doing in the last few weeks. So just replacing this term, so we now got f naught k2 into 1 minus omega square over omega 22 square. Now omega square, omega is the forcing frequency that is coming from external source, like an earthquake or a wind or unbalance or a misalignment or whatever that is, and the omega 22 is the individual natural frequency of the absorber spring and a mass. Clear? Individual means you have to remove it from the main mass and then measure its natural frequency, it's omega 22. This is the answer of the numerator. Now we have to solve denominator. For denominator, we just take the same thing. If I take k1 out of this bracket and k2 out of this bracket, so you get minus m1 omega square over k1 plus 1 plus k2 over k1. I am solving this denominator now into okay, this here become k1, and if I take k2 common from the second bracket, and if you can now remember it's simple bus minus m2 over k2 into omega square plus 1 minus k2 square. Okay, no, take the k2 and k1 common, k2 minus k, oh sorry, not minus, so also take k1 k2. Okay, so this is the numerator. So just look at the, I'll just take this step on the next slide. Okay, so this will become k1 k2, and it's a okay, so this will become minus omega square over k1 over m1. This k1 over m1 is nothing but the individual natural frequency of the main mass and spring, which is omega 11 square. Omega 11 is the individual. If you remove this absorber mass and spring, the omega 11 is omega 11. So omega 11 is the individual natural frequency of the main spring and a mass. Clear? Plus k2 over k1 plus 1, and it's the same thing, it's 1 minus omega square over omega 22 square, in the same way that we have done in the in solving the numerator. Divide by, if k2 is cancelled with the square, you get k2 by k1. So this is your solution for denominator. Just putting those solutions in your main equation of x1, what you get is x1 equals to, your numerator answer is f naught k2 into 1 minus omega square over omega 22 square what is the denominator? It's k1 k2 into 1 plus k2 by k1 minus omega square over omega 1 1 square into 1 minus omega square over omega 2 2 square minus k2 by k1. Okay. Okay, this k2 is cancelled with this k2 if I take k1 in the numerator. So what you get here is nothing but, I'm just writing in this step, will become f naught over k1. Clear? So this is what expression for the x1. Now just for the sake of further simplicity, I just want to find the, because k1 k2 or k1 is appearing in two places, so I have to just replace it in a certain way. So just look at this. So if I write k1 over m1 over k2 over m2, which in effect, so k1 over m1 is nothing but omega 1 1 square, and k2 over m2 is nothing but omega 2 2 square. Omega 1 1 is the individual natural frequency of the main spring and a mass, and omega 2 2 is the individual natural frequency of the absorber spring and a mass. So k1 over k2 into m2 over m2 over m1 equals to omega 1 1 square over omega 2 2 square. Clear? So now we call m2 over m1 as mu, which is called the mass ratio. Mass ratio means the ratio of the main mass, so ratio of the absorber mass, which is m2, divided by the ratio of the main divided by the main mass, which is m1. For all real time applications, mu should be less than 1. If it will be greater than 1, there is no advantage of you can say installing an absorber, because if that's the machine is 100 kg and you attach absorber mass of 200 kg, it doesn't make any sense because you're adding more mass. So the main idea behind adding a vibration absorber is that your absorber mass must be less than your machine mass. And if I quote you a real value, should be less than 0.5. This ratio, mu ratio, theoretically should be less than 1, practically it should be less than 0.5 or at most 1.5, not more than that. Okay, so what is, okay, so k1 over k2 is nothing but m1 over m2, or in other words, so square, so in other words it's mu times omega 1 1 square over omega 2 2 square. So k1 over k2 is equals to 1 over mu omega 1 1 square over omega 2 2 square, because we are interested in k2 over k1. So k2 over k1 is nothing but mu into omega 2 2 square over omega 1 1 square. This is the value of k2 over k1. Just put this value in the previous equation, you get, so I just take this equation, okay, so x1 is f naught over k1 into 1 minus omega square over omega 2 2 square divided by, okay, so what is k2 over k1? It's 1 plus k2 over k1 is mu omega 2 2 square over omega 1 1 square. This is the value of k2 over k1 minus omega square over omega 1 1 square. This is your first term, the second term is same, it's 1 minus, it's not whole square, sorry, 1 minus omega square over omega 2 square minus k2, it's the same value again, so it's mu omega 2 square over omega 1 square. This is the final expression of x1, you call it as A. And what is the expression for x2? Now look for the x2, the x2, okay, the numerator is different but denominator is same. So numerator value is nothing but this goes to 0. So we have in the numerator is only minus f naught k2. So it's minus f naught k2 divided by, okay, in the denominator we have k1, k2, clear, and then we have this whole term 1 plus mu omega 2 square over omega 1 square minus omega square over omega 1 square into 1 minus omega square over omega 2 square minus mu omega 2 square divided by omega 1 square. Clear? If you remember that this k1 appears because we have cancelled out k1 and k2 from the numerator and just removing k. That's why I've written k1 k2 here. Don't confuse with the first, this is after simplification. Clear? So k2 is cancelled with this, you get f2 is equals to f naught over k1 divided by the same denominator. So these are the two expressions for x1 and x2. Now we are interested, so as I told you in the start of the lecture, that this is a very beautiful equation, the x1, so first we take x1 and just give you an idea. So this is your expression for x1. So if omega is equals to omega 2, which means if your forcing frequency, which is omega, becomes equals to the individual natural frequency of your absorber mass, look at what mathematically numerator and numerator becomes. So this goes to 1, whereas the numerator goes to 0. So 1 is 0 divided by, okay, this term goes to 0, which means that whole term goes to 0. So get 0 over minus mu omega 2 square over omega 1 square by putting omega is equals to omega 2, and that is equals to 0. Now it means that if you design an absorber in such a way that its natural frequency is equals to the excitation frequency that is coming from external source, then the main mass actually has an amplitude equals to 0. And what is x2? By using the same condition, so it's become minus mu omega 2 square by omega 1 square in denominator, and in numerator look at this, because there is no this term in the x2, so this term remain, that is f naught over k1. This means that when x1 is 0, x2 has certain amplitude. It is not 0, it means that vibration has been absorbed from x1 to x2. That's why it's called vibration absorber. I again repeat, if you put a condition such a way that your excitation frequency, which is omega which is your omega becomes equals to the individual natural frequency of the absorber mass and spring, such that if you put this value, the x1 practically goes to 0, as you can see here mathematically. but your x2 gains a certain amplitude because not equal to 0, and in that particular case it's equals to f naught over k1 divided by minus mu omega 2 square over omega 1 square. Now what actually x2 do mathematically, so we'll just simplify this. If you look at this equation B, okay, equation C, this equation, so if I just simplify that, it's become f naught over k1 equals to x2 mu omega 2 square over omega 1 square. And if I just simplify that, simplify just to understand that what actually, how it absorbs the vibration, that is actually is you can say is hidden under this equation. So if I just simplify it, f naught over k1 is equals to minus x2 mu is you know is nothing but m2 over m1, k2 over m2 is sorry, omega 2 square is k2 over m2, omega 1 square is k1 over m1. If I invert it, so it's get k, sorry, it's m1, it's m1 over k1 because it's in the denominator. We take the numerator, it actually got inverted. So this is cancelled with this, this is cancelled with this, this is cancelled with this. With all these terms cancelled, you get f naught equals to minus k2 x2. Now what does this reveals? This reveals that when the motion of k2 and x2, or you can say the spring force, is such that if force is in the positive direction on the m1, the spring force actually, if or in other words, just to take it in simple words, so it's simple, if because f naught is a sinusoidal function, if f1 is positive upward, the spring force is actually downward because it's a negative sign, k2 x2. So whenever the f naught try to push the mass upward, the spring force, which is k2 x2, try to push the mass downward. And when the f naught try to push the mass downward because it's a sinusoidal force, at the same time k2 and x2 reverts its direction, try to push the mass upward. Because of this cancellation and because of this equality, the forces, this is the excitation force, this is the spring force, they actually cancel out each other. So this is f naught and this is k2 and x2. A force is pushing upward, so actually the answer is 0. So we have 0 vibration at m1. Similarly, when force is pushing downward, the k2 and x2 acts in such a way that actually moves upward, and again the answer is 0 because both are in opposite direction. That's why by using this philosophy, we actually reduce the vibration of the main mass equals to 0. That is why it's called vibration absorber. I'm again repeating, whenever you whenever you actually put install a mass spring system to a main mass such that the excitation frequency that is coming from external source become equals to the individual natural frequency of k2 and m2, then what happens is that your x1 goes to 0, your amplitude of main mass goes to 0, which is actually vibrating before, but your actually k2 your main m2 got some amplitude which you can also control by properly designing the vibration absorber. Now it's also called tune mass damper, and if you look at this word, and this will actually correctly fit into the definition, that is, tune means you have tuned the frequency of the absorber. Mass damper means your mass actually performs damping. Your mass actually acts in such a way that actually it reduces the vibration, which is the purpose of a damper. That's why it's called tune mass damper. Tune means it's set to a certain frequency. Is it tuned to a certain frequency? That is omega is equals to omega 2. And mass damper means the mass acts in such a way as a damper. Now just quickly to give you an idea that what is the importance of this. So this is the first picture. This is actually the this is type A 101, which is the largest now it's the second largest building in the world, located in Taiwan. This is actually a financial hub of Taiwan. It contains 101 stories. People say it's 101 stories. Or if I just zoom this picture, so it's about 87 floor to about 91 floor. In 4 floor, this is the tuned mass damper. This is a tuned mass damper attached in the 87th floor to almost 91st floor. And look at these floors. This is the 1 floor, 2nd, 3rd, 4th, 5th, and even up to 6 floors. The tuned mass damper is attached. This damper or vibration absorber attached, so that if there is any wind vibration that causes this, because it's a very high rise building, skyscraper. So if there is any vibration because of the wind, the vibration, this vibration absorber is tuned in such a way that to absorb those vibrations. And because your main mass is your building mass, which is M1, so if you design this tuned mass damper in such a way, as we have discussed before in this lecture, then you can actually reduce the vibration of the amplitude of this building to a very small value. Clear? So this is the one application of the tuned mass damper. The second application is basically in the transmission lines. In the transmission line, there is also a problem that because of the wind flowing across these wires, it tends to vibrate because of the flutter and sometimes galloping. So because it is basically a high frequency self-excited vibrations, so you can see a small dumbbell shaped masses are attached. These are basically tuned mass damper vibration absorbers, that if there is any vibrations in the cable because of the wind, so these small actually masses, or you can say absorber, actually tune to certain frequency that absorbs the vibration from the cable and does not allow it to vibrate. So that is basically the main application of tuned mass dampers. Okay, I just show a video in which you can actually see that how it actually works. The tuned mass dampers, if actually I can play that video. Okay, that's good. We just pause this. Okay, in this we have, this is mass 1 and this is your absorber mass. Okay. Clear? So this is your absorber mass. Now what he is doing actually, he is trying to look at this, is try to so this we have unbalanced mass on this main mass and spring. So he is finding the natural frequency such that if the excitation frequency, which is the rotational frequency of this unbalanced mass, become equals to the natural frequency of the K1 and M1, it tends to resonate. So look at this, its very high amplitude actually gives you an idea that it actually is resonating. Clear? Look at this. He is changing the look at this. This is a very high amplitude. Look at this. So it's a basically a resonance. Now at the same time, he attached a tuned mass decalculated on the previous equation, and look at this. At same frequency in which the mass is vibrating before at a very high amplitude, actually reduces to almost 0. Look at this, the amplitude is the same frequency, but now you can see your X2 starts to vibrate. That is an advantage of using a vibration absorber. Now the difficulty is that if you detune this, which means that if you slightly change omega, then there is a chance that both can excite. So this is a very big problem with the vibration absorber, and I'll just explain you in the next slide, and that is okay. Yes. So what you really want is if I just draw a line here, sorry, if I just draw a line here, so what happens is, because your omega becomes omega 2, so this is x1 k1 over f naught. This is basically the same equation. If you remember, this is x1 equals to f naught over k1, and the same thing here. So what I've done is just taken f naught in the denominator, so this will become transfer function, or the ratio of output over input. And what happens is, now at resonance, which means that when your omega is equals to omega 2, which is equals to 1, your amplitude of x1, which is x1, practically goes to 0. Look at this point. Look at this point. It practically goes to 0. That is the main purpose of vibration absorber. But because now become a 2 degree of freedom system, now it has two natural frequencies. One is below, that is about 0.8, and second is about 1.25. So you can't say its natural frequencies are gone now, because it's a 2 degree freedom system, has two natural frequencies. Now, one of the most difficulty in using absorbers, that absorbers operate in a very narrow range, which means that if you can say this is your actual range of operation of the vibration absorber, which means that your omega by omega 2 can vary from 0.8 to 1.25. In this range, your amplitude, but not practical, is even smaller than this. Sorry. It's only this range. It's only this range. This range, which is roughly from 0.9 to 1.1. I'm just giving an idea that if your omega changes abruptly from 0.9, lower than 0.9 or larger than 1.1, the system can actually resonate. But if a system is at resonance, which means that, okay, the most important thing here is that omega 2 to omega 1 is also 1, which means your omega 1 is also equals to omega, clear? Which means your actually main mass is also resonating with the forcing frequency. Then you add, I just explain again. So let's say we have no vibration absorber, and the omega is acting such a way that this system K1 is resonating, okay, is equals to omega n. So we add a second Springer mass is tuned to such a way that its frequency equals to omega, and in that certain application then x1 goes to 0. Now absorbers are generally used when the system operates near resonance. I am again repeating, absorbers are generally used when there is a chance that system operates at near resonance and you can't able to change omega, neither omega n, which is the natural frequency of your main mass. So then you used absorbers. If you can have a freedom, as I told you in the start of the lecture, if I have freedom to change omega greater than 3, there is no need to use an absorber. You increase the ratio, amplitude become very small. But in certain cases in which, like as I told you in the building, because you have a variable wind velocity, then you have a variable frequency, and maybe they find out in certain scenarios it can become equal to the one of the structural frequency of the building. So that in that particular scenarios, because you can't change omega n, because it's a very large building, you can't change stiffness and a mass to a huge value. Similarly, you can't have a freedom of omega. Why? Because omega is due to the wind and you can't control the wind speed. So what you can do then, you actually put an absorber that if the system tends to resonate, at any excitation frequency, then your absorber actually try to absorb those vibrations and put your main mass vibrations equal to a minimum, practically and theoretically equal to 0, so that your body will not vibrate. Now this is the main idea of this lecture. I hope you understood this lecture till now. The next time we will solve some numericals, and then we'll use this graph and the graph that will explain you in the next lecture. So hopefully it will help you to understand how to model the vibration absorbers and how to use it to our advantage. Thank you very much. Allah Hafiz.